The following animations show actions a manufacturer can take to manage the risk when their vehicle ends up in a potentially dangerous situation. For all of these, we're looking at what happens if the user in charge does not take control of the vehicle when requested by a transition demand. The first example is a reactive minimal risk maneuver because the automated driving system exceeds the normal limits of the conditions that it is designed to operate in. We start with a common driving scenario. The vehicle is making progress on a motorway and is experiencing light rain. As the vehicle continues, the rain becomes heavier and the vehicle enters a storm. It is unable to cope with the resulting reduction in visibility. The user in charge is requested to take control but fails to do so. The automated driving system now has to take the decision to maneuver the vehicle into a safe condition as it is unable to continue to make progress. After indicating this to the occupants, the automated vehicle slows down and pulls into the emergency lane and comes to a stop, switching on the hazard flashes to warn other road users.
Hello, as Head of Innovation for the Government Centre for Connected and Autonomous Vehicles, I would like to introduce you to some work we've commissioned from the CPC to help government and developers consider safe behaviour in the development of vehicles with self-driving features. As the UK seeks to improve road safety and how people move across a variety of modes of transport, active, public and private, it is vital that any development of self-driving vehicles has safety at the forefront. Minimal risk manoeuvres are an important part of ensuring the safe operation of self-driving vehicles. You've just seen a short video of one example of an MRM. This is a simplified scenario, but highlights the complexity of these manoeuvres and why CCAV considers them so important to the delivery of safe self-driving. The CPC-led SafeMRX project is considering the wide range of scenarios and circumstances that may result in MRX while helping the entire ecosystem consider what appropriate and safe manoeuvres should look like. This report will help to inform our thinking as part of the government's plans for assuring safety and security under the CAVPASS programme.
Let's imagine the same scenario again, but this time the manufacturer designed the vehicle so that it gets advanced warning of the rainstorm. Thanks to vehicle-to-vehicle connectivity, warnings are received from vehicles further along the road that there is a heavy rainstorm. The user in charge is requested to take control but, again, fails to do so. The automated driving system has a few more options this time. It is able to continue to drive and execute a different manoeuvre, which results in an even safer condition. Having issued the warnings to the occupants, the automated driving system continues to the next exit, or service station, and parks the vehicle in a safe position off the motorway.
A minimal risk manoeuvre is a complex set of activities that requires not only a highly technical solution of sensors and computers, but also needs to consider the human as part of the system. As humans, we perform a complicated and coordinated set of actions when travelling in a vehicle. Not only are we often physically manipulating the controls in our upper and lower body when driving, but we're also looking out and processing the visual information in our surroundings. This can both be inside the car, such as the displays and dials, and outside the car windows. There are also elements, such as the sounds and feelings sensed through the vehicle. For instance, vibrations, wind and tyre noise, and then there's also the additional challenge of navigating, decision-making, and predicting what other vehicles and road users may do. How will I respond to them, and how will they respond to me? So when a minimal risk manoeuvre occurs, how will people respond, not only in the car, but those around? How do they know it was going to happen? Do they take over? Can they take over? Key to understanding this is system and situational awareness and the level of mental workload for someone in the vehicle. There's been a lot of research around autonomous vehicles, and opportunities remain to gain a greater understanding around the human factors. How will humans respond to autonomous systems? How will they react to the decisions they make? How can someone rely that an autonomous vehicle will behave in a certain way and reliably? And how do you build trust? And how do we know that people won't abuse that trust? The work we've performed has aimed to highlight some of the key learnings and challenges from across industries. Not only the automotive industry, but also those such as aviation and manufacturing, to understand how cooperation has been built between users and automation. Elements such as the clarity of communications, consistency, reliability, and the training that people need were some of the key highlights. We also looked at different ways of breaking down how someone might process a minimal risk manoeuvre, what interfaces, behaviours, symbols and messages might need to be integrated in order to optimise the effectiveness of the system and maximise the end user understanding.
This final animation demonstrates a scenario where the vehicle avoids the need to do an MRM entirely. Following an upgrade or redesign, the vehicle is fitted with an additional sensor which improves the ability of the automated driving system to negotiate the heavy rainstorm. In this case, the vehicle continues with caution through the storm before emerging on the other side. This means that it avoids the risk associated with doing a handover or MRM entirely. These are just 3 examples of what the vehicle designer can do to make their vehicle safer in circumstances such as this. There are several more. We have identified 6 in total during this project, and you can find out more at our website.